Okay, can everybody hear me? Excellent. Okay, first I want to welcome everybody back. I see looks like we have about half the class so far, so I think we'll have some more stragglers pulling in here. We had some pretty good participation last week, so I'm expecting more this week. But we'll go ahead and get started here a little bit, start doing some intros and Q&A stuff. First, I see the one question right up the top of probably on everybody's mind, and that is about going over exam number 2. And so what I'm going to do is I'm going to go ahead and release my grading notes so you can see what the answers were, the expected answers were, and then that way you have some idea what's going on. And then what we'll do for next lecture is you can then have, group type of questions as far as, if there's something that you want to go over, you see the answer, but you don't understand, you want some further explanation, we could do that. The other thing, also topic of exams, is that you'll see that I have given you some additional points for exam number 1. You're welcome. What we're going to do, though, is we're going to do something a little bit in addition. Actually, I don't think of it as an addition, but we're going to do something just a little bit different. And that is we're basically going to retake one of the questions on the exam as a quiz. I'm going to do that because it was evident that all but a few of you were really struggling with one of the questions on the exam. And what I would, it's really important that you have this concept down. So what we're going to do is we're going to hold a quiz. And in the quiz, what we're going to do is we're basically going to be re-quizzing you on that one question. Now, it's not going to be that exact question. I'll have to come up with some different code for you to work with, but it's really important that you get the concept of being able to determine addresses and be able to generate assembled instructions and as well as the organization of it. So we're going to plan on doing that. Okay. Okay. So I'm sorry. I probably should explain this image I put up for you. I like this one, and some of you have seen this. Anybody know what this is? This picture here is of what it represents? Great. Some great answers. Keep them coming. So the first question somebody asked about was, what question was I talking about? That was number 6. So question number 6 on the exam number 1 is the one that we will be essentially retaking. So this picture here is all of the waterways in the continental United States. And it's kind of cool. It's done as an illustration just to help visualize, how some of these tributaries end up into some of these major rivers that then will go back out to the ocean and recycle and continue that whole process. But I thought it was really interesting because it kind of shows how the different waterways are getting fed and how they move throughout the U.S., which is, as you learned in K through 12, was a very important part of our whole industry and our whole agriculture system and how we evolved and evolved the country, which I thought was pretty cool. So I thought I'd share that with you. Okay, so let's go ahead and change our share here. Okay, so as a reminder, and I know you probably have this open already, and we're going to be focusing on compilers here for the rest of this semester. And you'll see that we start off with chapter 5, and then we go into some slides on some discussions using some systems tools such as Lex and Yak. I will take a look at this. I might revise it a little bit depending upon how the next couple lectures go. We'll see. But that is the plan, and then we'll just go from here. The whole idea with the rest of this semester, though, is focused on compilers, how they're constructed, the different systems tools that comprise a compiler, and understanding what they are, because they then become interconnected with a bunch of other systems tools that you might or might not be familiar with. And so I want to expose those to you because they're important, because they help you as additional tools when you're developing code and debugging code, particularly when you're trying to debug a running system that you've been working on and building, and it works in some environments but might not work in some other environments, and using some of the systems tools that are specific to those particular hardware operating systems combinations are going to be very valuable for you. It's like libraries in a sense that when you're writing code, you want to be able to link to libraries and reuse libraries instead of having to rewrite that code every single time. Well, the same thing's going to be true with some of these systems tools, is that we're going to build them, we're going to compile them, and then we'll just reuse them, even in tools like compilers, or reusing some tools to help provide that kind of optimization from writing a basic compiler and getting it to work with different hardware combinations and different operating systems combinations, different operating systems versions. All of those things are going to come into play when we start talking about compilers and their construction. So the goal of this class isn't necessarily to make you proficient in understanding how to actually write the compilers, but it's going to give you an appreciation of what they're doing and a basic understanding of how they work. We do actually have a full semester class in compiler construction, which goes into it in pretty detail. But this is going to get you started and introduced to it so that you could go into a semester study if you say, hey, this is really what I would like to do. I would like to get into this more. And it's probably a good time to mention a couple things about computer science that you might or might not have thought about, or may have been discussed with you with other classes or not. But one of the, and we talked earlier on about, computer sciences can go off and write code. Yes, we can build software systems, we can design systems, build systems, test systems, we can do all of those things. But you could also write software without having a computer science degree. You could come in with other degrees or even non-degrees and still be able to write code. But what our computer science program is doing is giving you the skills to be able to do analysis and do design and be able to study and advance the technologies that we use as computer scientists, like compilers and like these systems tools that we're talking about, in addition to certainly things like machine learning tools and all of these advanced operating systems concepts that are going to go into, that are going into the newer types of computers that are being studied and worked on these days. So that's one of the reasons why it's important to understand compilers and why it's a fundamental topic of discussion in computer science programs. Okay, so that's a little bit of background. That's why we're doing this. I always find that it helps to understand why we're doing things. That way you can put it in the proper context, I think, and help. Okay, so let's go ahead and first off, start off with any questions. Okay, so the mini exam, okay, 2 questions. One is the mini exam. Those are basically bonus points. So that's just going to be added on top of whatever points you've earned for each of the exams. As far as the mini quiz, what I'm going to do is I'm going to increase the number of, I'm going to increase the number of points that you need for calculating the grades to accommodate the points in the mini exam. I haven't quite decided yet how many. It's either going to be 15 or 20. I think it's going to be 15. And then I'll share that with you as soon as I resolve that. As to when, it will probably be at about, well, I haven't decided yet, but it's going to be like 2 weeks from now, 3 weeks from now at the most. But no, it can't be 3 weeks. It has to be 2 weeks from now. So I'm going to do the next quiz as a standalone quiz. It's not going to be part of an exam because I want you to focus on just this one thing. And actually, I think it's going to be better for you because what that does is you can then focus on just the one topic of discussion that I want to quiz you on. And that way you're not having to go through a whole couple of chapters of material trying to prepare and include that one topic as well, which everybody was struggling, not everybody, most of you were struggling with. So I want that to be focused. And as I said, I'm tacking on the extra 15 points. It could be 20, but I think it's going to be 15 points. I'm going to tack that on to the amount of points you are going to earn for your grades. So that will be part of a new grade, essentially. I'm going to put you on pause here 1 minute. Okay, I'm back. Yes, one more quiz, one new quiz added on. No, the new quiz will be specific to the problem number 6 on exam number 1, as I mentioned earlier. Okay, let's go on to chapter 5. Okay, change my share. Okay, chapter 5. So as I mentioned, what we're doing in this chapter is we're going to learn about and understand what a compiler is and how it is constructed. And this is the basic organization of most compilers that you're going to see right here in this slide here. So I've created this slide and we're going to go back and forth between this slide as we go through the different components of a compiler so we can understand where it is in the compiler construction, so you have, again, a better understanding of that particular subcomponent. Okay, so right at the top, you can see, where's my little pointer? There we go. Got it. So at the top is your source code file itself. So that's where we're going to start. And we're going to look at how the source code file goes through each of these subsystems and components, as well as how is that source code file being transformed. What does this subsystem generate? The lexical analysis generates these tokens, which the syntactic analysis used to generate either a parse tree or a stack, which the semantic analysis section will use to generate the intermediate program code, and so on until we get out here to the executable code itself. Okay, there's some data structures that are going to be shared between these different subsystems. They'll be created by and shared with these different subsystems, and we'll talk about those as we go along. So let's start off with a few definitions. the lexical analysis, and we're going to go into great detail. This is a summary collection of definitions here for each of these different subsystems. And the lexical analysis subsystem is going to take and use scanners and tokens. Syntactic analysis will use parsers, grammar, semantics, and so on. So we're going to learn about all of these subsystems and what they do and how they do it. These are some of the terms that you're now going to learn and understand as we go through this discussion. A couple of things I should point out, and we'll talk about them in detail as well as when we talk about each of these different components to these subsystems. There's some very specific definitions of some tools that we're going to use, and we'll be using these throughout the rest of the semester. So starting off then with the first subsystem, which is the lexical analysis phase of our compiler. It is often referred to as the compiler front end. And what it does is it has all of the things that you are familiar with that particular program language built into its rule set and its toolkit. So the things that make C or C++ or Fortran or Java familiar to you is all going to be interpreted by this front end component, this lexical analysis phase of our compiler, that's going to then use some specific tools that we're going to talk about here to recognize the input that you have provided through your source code. So first thing it's going to do is it'll read, or scan as we call it, your source code file as the input for what this translator function is going to do. It's going to analyze what it has scanned by recognizing input, if it could recognize it according to the rules you define for this language, and it's going to classify it. Because as we scan input and we recognize it, we then classify it as entities of specific types so that we can say, yes, this is correct input based upon the rules for this particular language. So the types of things that we could recognize and classify are identifiers, delimiters, operator symbols, numbers, keywords, noise words, comments, blanks. All these types of things are items that we can create rules for so that we can recognize it and classify it as any of these things. We're going to use some tools, as we state here, we're going to use some tools to help us do that. FAs are finite automata. FSAs are finite state automata. They're like finite automata, except they're stateful. And then another tool is the Backus-Naur format. So we'll talk more about these in details in following slides. So once we've done this, once we've recognized the input word by word, or delimiter, all of these different things that we can classify, then we're going to generate tokens. These tokens are some internal representation that we are going to convert these classified entities into, okay? And that is what we're going to use to be in the next phase of this compiler to further get to the point where we're generating that machine code that we've been working with up till now. So let's take a look at the first tool, the most simplistic tool, I should say, first. Okay, and that is the BNF, or Backus-Naur form. So the way that read the Backus-Naur form is you're going to create some rules. These rules are going to have names that we put within the angle parentheses, the angle brackets. Then we do : equals. So we say rule ID is defined to be, and then we have this stuff over on the right-hand side. On the right-hand side, what you see are things, in this case, things separated by bars. These bars you would read as an OR function. So in this case, let's come down to the bottom first. The most fundamental rule we usually put down at the bottom, and the most fundamental rule here we define as a char. So rule char is defined to be lowercase a or lowercase b or lowercase c, so on, so on, so on, so on, so on, or uppercase b, a, uppercase b, uppercase c, so on, so on, so on, so on, so on. The rule above it is a rule that recognizes and classifies things as digits. Okay, so a digit is defined to be a 0 or a 1 or a 2, so on to 9. So a couple things here. I think you're kind of getting the picture here. Is that you can also build rules using previously defined rules. So that's where we saw at the top of the list. We had the rule ID, where ID is defined to be a char, which we define down here, or an ID followed by a char. We're defining ID right here, so we can, if we've classified something as an ID before and there's a char behind it, we can then recognize that and classify that also as an ID. Or it could be an ID followed by a digit. So we could have something, like we said, classified as an ID, and it could be followed by a digit, in which case we can still recognize it and classify it further as an ID. Now, this may seem very simple to you, and this is a simple example. Some of our BNFs can get fairly complex, but it's very important because you have to be very explicit with this. As you saw in this case here with chars, where we differentiated lowercase from uppercase, and if we had not created the uppercases, we could not have accepted and classified any uppercase characters that were in the source code file. We can only do that because we created a rule, char, that can accept it. So if you left off one letter, lowercase f, in your rule for chars, then your source code could never include anything with the letter F in it. It would get rejected by the compiler. So it's very important that you are very explicit and very much attuned to details when you're building these rules, because the compiler will be constructed using exactly what you defined in here. Don't like 0 as a digit? Just leave it out. Of course, you might make some programmers mad, but that's how you do it. Okay, and we can also create more complex constructions than a single rule or a rule followed by a rule immediately. We can create more complex ones, and we'll see some examples of that, but this is just to help you understand the basics behind BNF. Now, I will explain that there is a different variant of BNF called eBNF, or enhanced BNF, and what that does is it allows us to write some more complex rules in a more simplified manner, because as we start getting more complex rules defined here, we find that we needed some more notation to help us make it more readable, and so the eBNF did that. So in this example here, where we take a look at ID, where we saw some similarities that we were kind of repeating here, this is an example of what eBNF can do for us to help simplify reading this and writing the BNF rules. So in this case here, we simply said, and we kept ID, that's the rule that we're working on. So ID is defined to be a char, just like we set up here. But instead of an or, and we create this case and this case here, what we did instead is we used, as you can see here, the curly braces, and we can say it could be a char followed immediately by a char or a digit. But wait a minute. If we had said that, then we couldn't accept just a char by itself. So what eBNF also does is it creates the symbol that we can use with the curly braces. And in this case, what the star says, there can be 0, 1, or many instances of what is inside the curly braces. 0, 1, or many. So if we have 0 cases of these, then we can accept a char all by itself, just like this rule did here. If we have 1, a char, or a digit, we can accept it. And we can continue accepting chars and digits and keep doing that over and over. So we can just, as long as we're creating this ID, this identifier, right, it's going to follow this rule. So this is, I think, a pretty simple way, or a more simple way, I think, to see what some of these rules are doing and define what these rules are doing than stringing them out this longhand notion like this, especially when they start getting really complex. So we'll see a lot of people using eBNF if they're using BNF for this specification. And that's the main reason why. But we can accept both. You need to understand how to read both, just like you need to understand how to read and write in multiple compiling languages. So Raul asked, do all regex type notations apply to eBNF? Yes, you can use it for any regex. Regex means regular expression. So if you're not familiar with that term, that's what we're going to be using as the language of these systems tools that we're talking about. We're looking at regular expressions, how to express them and evaluate them so we can accept your inputs, your source code. Okay, any questions on this fundamental language here, BNF? Got it? Okay. So now let's take a look at another tool, and that is the finite automata. Now, some of you, a lot more of you should be familiar with this. All of you should be familiar with this, but this is, in case not, this is a state model, right? So we have, in a state model, we have to have an entrance event, and that's what these lines are events, and then we have the state, right? So the first thing that happens is we're going to get started. We'll go into state 1 so we can accept some input as we scan it. Now, I think it's worth going back here and pointing out one more thing. It should be obvious, but I want to make sure you understand this. We're defining an ID is defined to be a char, or if you come down here, is defined to be a char all by itself, or a char followed by either a digit or a char. So that means all IDs will start with a char. You cannot start an ID with a digit. Okay? So we're going to stay consistent with that definition of an ID here. So keep that in mind. So we go into state 1, and in state 1, we need to recognize a char. And a char is defined to be an A through Z lowercase or A through Z uppercase. It's probably worth pointing out as well at this time that when we mentioned that we specifically had to write everything out, that means we can't use things like a simple dash from A to Z here, lowercase, and then A to Z here, uppercase, because we have to explicitly include every symbol, because that's what this is a symbol, that the scanner is reading in to be able to classify it as one of these rules. So it has to be stated out. You can't take shorthand, shortcut, rather, type of tricks. But in our FAs, our finite automatas, we can do that. So that's what we're saying here, is that anything lowercase a through Z or uppercase a through Z, we will accept it, transition from state 1 to state 2. And in state 2, we could continue to recognize additional things behind that initial one, as long as it's an A through Z or A through Z, or now it could also be a 0 through 9. So we're stating all the different things that we can accept and still classify this as an ID. Okay, and that probably should have I probably should include that here just to make that very clear that we're talking about specifically the rule to accept and classify input as an ID. Because if it was some other rule, then obviously the event transitions would be different. So transferring from state 1 to state 2 was important because that's the only way we can force that first appearance to be a char. And then we're simply transitioning back into state 2 as long as it's a char or a digit that we are reading and classifying as making this ID, however long the programmer made it. Okay, if it's not, then we're done. We're kicked out of this part of the state model. We'll have to transition somewhere else. Okay, so that's all we can do here for an ID. Does it make sense? I'll take that as a yes. Okay. So FSAs, we'll go into those later. The key thing I want to do next is start putting together a larger construct, larger definition here of how we can specify and build, don't go there yet, specify and therefore build this front end part of our compiler. Which subsystem are we in? Anybody? What part of the compiler are we in? Lexical analysis, but we're not sure. Okay. You're absolutely right. And I'm going to be doing this throughout this whole discussion because if we don't understand the context with which we're working, then it can get very confusing. So you need to make sure that as we're defining these different subsystem components, we know what we're trying to accomplish here. So yes, we're in the lexical analysis phase, which means we're trying to understand what this input is. So what we're going to do is we need to generate tokens in this phase. We're reading the source code, we're generating tokens, and now we talked about these 3 tools that we can build these rules with. Okay, so we're going to build a bunch of rules. What can we accept and classify things as? Well, we talked about the identifiers up to here. And notice here the definition of identifiers, which are names, right, is up to 31 combinations of characters, digits, and underscores, as long as it starts with a char or underscore. Now, one thing I didn't mention here is that we want to take a look at a familiar language. So we're going to take a look at the C programming language here. And the C programming language, we want to see if we can define it according to some rules. All right, so that's where we came up with these definitions for 31 chars length, as long as it starts with a char or underscore, those are the legal names that we can use for identifiers. And so that's what we're going to do, is create that rule. But we have some other rules too. Some of the most fundamental rules are the actual alphabet. Okay, and we saw examples of that in the BNF, but of course in C, the alphabet's a little bit bigger. In addition to A through Z lowercase and A through Z uppercase, and the digits 0 through 9, we also have some special characters that we can accept. And these are the special characters that the C programming language can accept. And so we're going to need to define our alphabet to be digits, chars, special characters, and then build the rules that can accept each of these. Once we've done that, we can now accept that input and start to further classify it. Now, the next thing to be concerned with here, as we're talking about rules for classification, I'm jumping around a little bit here because I think it makes sense to talk about it this way, and that would be the operators and punctuators. Now, C has simple operators, semicolons, commas, plus, minus, all the arithmetic expressions, but it also has complex operators That is, these combinations of two or sometimes three special symbols that combine together into a single operator is a complex operator that has a specific meaning and operation that we would perform in the C programming language. So we need to be able to build rules that can accept and classify these combinations, these symbols by themselves or together in sets of two or three. So we're going to need to find those in that term. The other thing that's important when you were studying your languages, of course, in your language class, computer languages class, is that every language has a set of keywords, which are important to know because, well, you can use them to perform specific built-in operations for the language, but it's also reserved words that you cannot use as variable names. And so in the case of C, this is the collection of keywords that make up the C programming language. So that means as we're defining this Lexer, as somebody had referred to this, lexical analysis tool, we need to be able to recognize this combination of chars, this combination of chars, all of these different combinations of chars to say, hey, if I've got this, then it's a keyword. It's not a char, it's not an ID. It's going to now be a keyword. Okay, so we're going to have to build the logic behind some of these rules to help us be able to do that. But we have to have a rule that can accept and classify these combinations of chars to be able to classify those as keywords and accept them. So in addition to these classics, the alphabet, the keywords, the operators, the identifiers, most programming languages have other things that they want the compiler to be able to recognize and classify input as well. An example in the C programming language, of course, would be things like integer constants, floating points, character constants, literals, like we saw before, and these escape sequences that you've hopefully been using, and if not, you'll be using, as you should have been using, I think anyway, in program number 2 here, assignment number 2, using some of these escape sequences to recognize and operate on input different ways. Okay, so if you're going to define that as part of the language itself, that means we also are going to need to construct rules that can accept those sequences and classify them as whatever these different things are. In the case of C, it would need to be able to recognize input that matches the criteria, the definitions for each of these 5 different rules. All right, so we have a question from Trevor here. What part starts to determine what a symbol means? For example, appears as both in the alphabet and an operator. So we're going to take a look at that. We're going to walk through that. That's a great question. So right now we're just trying to define rules that can recognize one. And now that you've seen that, yeah, we might have a problem here where something could be one or the other. How does that work? We're going to walk through that. Excellent question. Okay, whoops, I'm going too far forward. I gotta trying to drag my screen over so I can see it better. Does this coding scheme also take comments into account? Only if you build that in. So if you want to build in a language that accepts comments, then you will have to define that. What is that rule? And then in the case of C, of course, that would be the slash followed by the asterisk, and everything following it is a comment until it encounters an asterisk followed by a slash. C++ is a little bit different, right? Because there you have 2 slashes, one right after the other, complex operator, if you will, but it's not a complex operator, it's a comment. And it goes until it hits new line, right? So you have to take what your language requirements are and then build your rules to recognize exactly what the language requirements are. Okay, so now let's take a look at our language here using a finite automata. Okay, so we're going to have a start event. Okay, we have some input coming in. We transition to state one. So state one, what we're going to do is we're going to read that first symbol, and we're going to see if we can recognize and classify it. Well, if the symbol was an underscore, then we could transition from state one into state two, because a ID, right, can start with either a char or an underscore, which is what this says here, right? A char, which is A through Z, lowercase, A through Z, uppercase, or an underscore, will transition us into state two. So if the very first thing is reading, then is an underscore or one of these symbols here, then we can transition to state two. And if it's followed by underscores, A through Z's, lowers and uppers, or 0 through 9, we can do that just like we saw in the earlier FA. What happens though if the first thing it read was a digit? Well, if it was a digit, it cannot be an ID, so it can't go there, but it could go into transition to rule 3. Or rule 3's, excuse me, of state 3, sorry about that, go transition from state 1 to state 3. So if it accepted a 0 through a 9 symbol, then it transitions into state 3, and we're saying, oh, we could build an integer constant from this. And the integer constant can be any subsequent number of 0 through 9s following that first one, so we can build up this integer constant number. And this is why it's an integer. It has to be a 0 through a 9. Cannot accept a period in there. That would not be an integer. Well, if the input was different, if it was semicolon, comma, parentheses, any of these symbols here, right, we would transition from state 1 into state 4. Now, it has to be a single one of these symbols, and that is a terminal state for, these were all terminal states, remember, but we can have multiple instances of these symbols, so this number, this integer constant could be as long as it needs to be. Same thing with ID, up to 31. We didn't talk about how to stop at 31 yet. We'll come back to that. But here, if we have a single one of these specific operators here, we can accept it as a unary operator, and this is the collection of unary operators that we had defined in the previous slide. However, if we're in state 1 and we recognize and accept one of these symbols here, okay, these symbols here could be unary operators, but they could also be compound operators if they're followed by an equal sign. So we'll take any one of these symbols here, which is different than this whole collection here, and we could transition into state 5. Once we're in state 5, we can stop here. That's why that's a terminal state, or we can accept an additional equal sign. If we used any one of these symbols followed by an equal sign, it transitions to state 6, and that's our terminal state there, and we can accept that as a compound operator. Okay, so it's a little bit more advanced than the first FA, but it still hasn't answered that question. What if we recognize something and it could be classified as more than one state? And we'll talk about that again, like I said, coming up soon. But this hopefully helps us understand how we might want to design our state model so that we can make it as unambiguous as possible. And that's what's really going to drive a lot of this discussion that we're going to have about these grammars. And that's what we're talking about as a grammar, some rules for defining these rules. And we want to make them either ambiguous or unambiguous. It's best if we can make them unambiguous, but there's some trade-offs. And we're going to be talking about, well, we talk about trade-offs to ambiguous grammars versus unambiguous grammars throughout the rest of these discussions. But for now, I'm introducing the concept here because we could have defined all of the unary operators up here, but then we would have had to figure out some way to accept the compound operators for those that ended with the equal sign. So this is the most clear way to do it. You break out those unary operators, which can only be unary operators, and you define them here. And those that are ambiguous, they could either be unary operators or compound operators. Define those in their own rule. Or in this case here, this rule with these two states. Does that make sense? One thing about these rules that we're building, whether you're using BNF, FAs, or FSAs, is that at some point we're going to write code to implement this stuff. And so we want to choose the tool that is going to be the easiest to understand, the clearest to write the rules and define them with, so that we have the best opportunities to write good code to implement those with. All right. So now let's take a look at our scanner. And what our scanner is going to do is it's going to recognize and classify those basic things that we just talked about. Okay, so let's go back to BNF now, because I think it's a little bit easier to understand how to generate code from here, because we're going to introduce some other key concepts that we haven't before we can get to the point of cutting code, which is, I think, a lot easier to see with BNF than it is with FAs. So let's expand our BNF from what we saw previously, where we had chars, and we saw how we define chars. We haven't changed that at all. And we have digits, just like we defined digits before. We haven't changed that at all. And IDs, we modified it a little bit, right? Because this is for C. So we have a char or an underscore. Because remember, it could be one or the other. Or it's an ID, because if we accepted a char and classified it as an ID, we could come back in and say, an ID followed by another char. Yeah, we could do that. Or if it's an underscore, same thing, classified as an ID followed by a char, we can do that, or an ID followed by a digit. So those are the same. But since we can also accept another underscore, we need to have the ID followed by an underscore, so we can accept that in addition to a digit or a char. So we added that in there. Okay, so that was the change we made to ID. Now comes something a little bit different. Okay, and so let's start off down here, because the most basic fundamental things are at the bottom. We try to grow them up. So UBasic. UBasic are these special symbols that we defined as always going to be just one, right? These are never going to be a compound operator. These are unary operators. So we have UBasic or unary basic to say these symbols here, this or this or this or this or this or this, and so on. Okay, and then we have the U extended, right? And so these are those other symbols that can either be unaries or it could be compound. So we define those as U extend and U basic. So now we can start building rules to accept symbols as either a unary or a compound. Okay, so up to now we just defined these as these very basic rules, but now we need to actually be able to put them together. So for unary, right, what we're going to do is we can accept a UBasic symbol. UBasic symbol as a unary operator. That's obvious. Now, we can also take and accept a U extend. A unary extended set would be this. So any one of these symbols by themselves is a unary operator. Now look what happens. We said we can also have a unary followed by a UBasic, or we can have a unary followed by a U extend. You're scratching your head saying, well, wait a minute, we just said compound operators were always followed by an equal sign. Well, okay, let's take a look at that then. Okay, here's UBasic followed by the equal sound. There's your compound operator. Okay, and that's consistent with this, which is consistent with this set here. Okay, so that's all we're doing for that rule, is saying any of these symbols here followed by the equal sign is the compound operator. oops, one too many. Compound operator, U basic, that's these, followed by the equals. But going back to here, we talked about, yeah, we have those, but we have some other operators as well. The plus plus, the minus minus, we use those all the time, right? We have operations that we do, operators, excuse me, that we do that are not compound operators, but they have specific functions to them. So we still need to be able to recognize those and accept those. Okay, so we can perform those operations. So that's what we're going to do here with the unary operator, is allow us to say not just the ubasic or the uextend, but we're going to take a unary. It always will start with one of the symbols that we've already accepted, a ubasic or extended, followed by a basic or followed by an extended. Okay, so that's how we can create that. And then last thing is the integer constant. The integer constant, as you recall, must start with a digit. Okay, and now it's the 0 to 9. Or once we define that first one, that first digit we find, we classify it as an integer constant. So then we could take an integer constant that we've already classified, followed by another digit, and we can reclassify it as an integer constant so we can accept the whole integer number. And that's how you would read this. That's how you would write this. And yes, I will be expecting you to be able to read these. I'll be expecting you to write these. I'll be expecting you to modify these to do different things. Okay, comfortable with this? At least an introduction to it? Okay, so that was the purpose of the lexical analysis, is that we want to scan the input. We're going to use either a finite automata, finite state automata, or a Backus-Naur form set of rules to accept the fundamental input that we're reading based upon the lexical analysis that we do with these rules. And we're going to recognize IDs, digits, chars, integer constants, things like that. We're going to recognize and classify them as tokens. These tokens are going to be by type. These are the fundamental, just like we say right here, this is the fundamental construction that we're going to use inside the compiler. This lexical analysis is scanning it, and it's going to use these rules to recognize that input and classify it and generate classified tokens that the syntactical analysis tool can then use to further analyze what the programmer wrote to try to make meaning out of it that we can generate code with. All right, just like we've been talking about here. Any questions then on our Lexer? Our lexical analysis tools, its purpose, the three main tools that we have for implementing it, and what it generates. No questions? Okay. I think I'm going to hold off on talking about syntactical analysis yet, but this is the next piece, right? Just like you saw in that tree that we were looking at, where we're going to read those tokens that the Lexer had generated for us, and it's going to parse it, and it's going to further organize it so that the rest of the compiler can do its work. Any questions? This is all out of chapter 5, just like we showed in the syllabus. Other questions? I haven't set the date for the quiz yet, just as I mentioned earlier. I will do that before we meet again on Wednesday. Other questions? Okay, so I hope everybody had a great weekend. I know we were all told to stay home and it was all rainy anyway. So, yeah. Question about the first practice quiz. There were a couple of people who were not successful. They wrote email at the time explaining what their issues were. I'm going to allow them to retake the practice quiz, but if you did not participate in the practice quiz, I'm not going to rerun it just because you didn't participate. Practice quiz, mini exam, yeah, you can think of them as the same thing. I'm going to set up points, like 15 points for it, and it's going to be very focused. So yeah, they're equivalent. So we're still having an exam on the date of our scheduled final, kind of, sort of. I'm going to spread it out across a couple of days like I did with the exam number 2. That seemed to work really well. And I understand there's some people need that flexibility like we talked about the last lecture before the exam last Monday. So I'm fine with that. That seemed to work rather well. And that's a good reminder. I was going to ask you, I set up a topic and some of you responded to it, but if there's some things that you think I need to be aware of when I set up the next exams, please share that with me. There's a number of things that people have brought up, so that I'm mindful of. But if you discovered some issue that you had that was prohibitive or complicating things, do share that with me. And if it's something I can correct, fix, or work around, I will. If it's not possible, then at least I've had a chance to look into it before the next exam. Well, thank you. Yes, that's great to hear, because these exams, I really want to test your knowledge. I'm not trying to see if you can quickly adapt to a tool and make it work for you. Okay, I think we will call it a night then. I will go ahead and turn off the audio, but if I'll leave this window open, so if somebody has some further things they want to put into the chat window, they can, and I'll shut this down a little bit later. All right, thank you all. We'll see you on Wednesday.